Okay, I think I'm just going to go ahead and start just as people are filing in because I have a couple of things to say. So hi, everyone. Welcome to the Essex Seminar Series. My name is Kazi. I'm going to be the moderator of today's seminar. So today we welcome Dr. Magnusdottir, who's going to talk to us about the drivers of Southwest U.S. rainfall. So just as a reminder, this seminar is recorded and the video will be posted on our YouTube channel in just a couple of days. So a little bit about our speaker today. So Professor Gudrun Magnusdottir got her BS in physics from the University of Iceland, her MS in atmospheric science from Colorado State University, following which she worked as a meteorologist in the Icelandic Meteorological Office. She returned to Colorado State University for a PhD. She was a postdoctoral researcher at the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. She joined the University of California, Irvine in 1995, the year in which the program in geoscience became the Department of Earth System Science. Should be used to saying that. She is a professor and a past chair of Earth System Science of the Department of Earth System Science. She is a fellow of the American Meteorological Society. So everyone, thank you so much for coming, and please welcome Professor Magnusdottir. Please proceed.
Thank you so much, Kazi, and I'm happy to be here, even though I'm not in person. I'm with you over the internet, so it's great to be here. So I want to describe some of the activities in my group at UC Irvine to explore seasonal rainfall variability in California and the Southwest, or in the context of predictability, what might be gained in predicting California seasonal rainfall by improving prediction in the tropics and or in the high latitudes. So these are members of the team who have worked on this project. Yannick Pangs is a researcher. Cameron Dong is a PhD student who is in his fourth year, is doing really well, might graduate very soon. And Yuna Lim, she was a postdoc with us, is now at NASA Goddard. This work has been supported by the California Department of Water Resources. So first, I'll describe what may have been the role of tropical and high latitude variability on the 1980 to 2016 Southwest U.S. precipitation by using AMIP and what we call AMIP-plus experiments. I'll then briefly talk about biases in some of the S2S models, and lastly, describe a case study of the wet and somewhat puzzling water year 2017. So let me just state at the outset that we're not making any predictions here. Rather, we are exploring what might be gained by improving predictions in the tropics or in high latitudes for seasonal prediction of Southwest U.S. precipitation. In other words, we are examining processes that might or could be improved on in the models and would then result in better predictions. So it is convenient to characterize the seasonal precipitation by the cumulative amount through the water year. The dashed curve indicates the average for 1980 to 2016 with plus or minus standard deviation indicated by the pink envelope. Here are some recent memorable years. The top panels show two recent regime shift water years, 2012-13 on the left, when the season started out strong and then dried up in mid-season, and the 2013-14 that was dry throughout. So Lim et al. Describes how the rather wet conditions in late 2012 that were related to conditions in the tropical East Pacific turned to dry conditions in early 2013. And that was due to MJO teleconnection, so subseasonal variability then. Both years were part of the California drought years, and it stayed dry the rest of that year. Now below is the water year 2016. Two interesting years. On the left is the 2016 when we had the intense El Nino that resulted in absolutely average conditions in California, as you can see. And then the following year, 2017, we had pretty extreme rainfall throughout the year. So I'll turn back to these examples later on in the talk. So it is challenging to predict Southwest US rainfall as shown here. This is a figure from Kumar and Chen, 2020. And it shows the skill of the CFS version 2 seasonal forecast for predicting DJF precipitation over the continental US in hindcasts over 1982 to 2010. As you can see, the skill is pretty good over the southeast US. But if most of the other parts of the country, low skill, and in the Southwest US, this is the domain that I call Southwest US. So it's California, Nevada, Utah, and Arizona. The skill is only about 0.3 or so. So most of the skill for seasonal prediction comes from sea surface temperatures, in particular ANSO conditions or tropical Pacific SSTs. But the teleconnection is intermittent, as it is not always efficient in bringing precipitation. So as I said before, 2016 was a year when El Nino didn't deliver to the California and the Southwest, at least. So here we're taking a step back and trying to understand in idealized experiments how this could be improved on. In particular, what would be the benefit of improving model variability and representation in the tropics and in the high latitudes? So the model we use is the whole atmospheric community climate model, WACCM. It's a 2-degree horizontal resolution model and has a high top with 66 vertical levels, reaching to 140 kilometers. We use the specified chemistry option, and the external forcings that follow the historical values from 1979 to 2016. And we use the option in the model of prescribing the QPO according to radiosonde observations. So we have 4 types of experiments. The first is a standard AMIP-type simulation where we prescribe observed sea surface temperature and sea ice concentration to the model, so that the ensemble mean of these simulations is isolates the effect of sea surface temperature variability on the atmosphere. Then we have what we call AMIP-plus simulations. They're similar to AMIP, but in addition to prescribing sea surface temperature and sea ice concentration from observations, we prescribe atmospheric variability in certain regions of the model domain. So first we have the AMIP-trope simulation. That's where we prescribe tropical atmospheric variability. Then we have the AMIP-HL, or high latitude, where we prescribe variability in the Arctic. And then the simulation where we prescribe both, so AMIP-TRHL. We run 10 ensemble members for each experiment. And we use a nudging technique to prescribe atmospheric variability. So we nudge UV temperature and surface pressure towards a target state that consists of the model mean state plus anomalies from MERA2 at the 3-hourly timescale. So we nudge or relax the model towards 3-hourly MERA2 variability from 1980 to 2016. You can see the domain for the nudging in different experiments here. On the left is for trope, so that's in the tropical band and goes up to 150 hectopascal. For HL, that's the Arctic, so 65 north and to the pole. And then we prescribe, and that's up to 300 hectopascal. And then we prescribe both. In the last one, AMIP-TRHL. We use a nudging coefficient of 0.1, so that corresponds to 5-hour relaxation time. And at the edges, the nudging coefficient decreases to 0. So I'll present some results here. we have 10 ensemble members for each of the experiments, and we're looking at the ensemble mean. Now, of course, the main driver for Southwest US rainfall is the atmospheric circulation over the North Pacific. So here we really focused on atmospheric variability, and in the domain shown in this blue box. So when I do pattern correlation later on, it's in this box. But let's look here at how how the model in different configurations does. This is the Z500 anomalies, and this is the grid point correlations between Z500 anomalies in the ensemble mean of AMIP here, and the reanalysis. And this is for the full 1980 to 2016 period. And we have quite good correlation already by just prescribing SST and AMIP. Then on the right is the additional skill. So additional skill that we get by prescribing tropical variability in addition to the AMIP. This shows that we increase the skill, especially in the region of the subtropical Asian jet here. And this is important because this is the jet exit region, if you will. So it's interesting because it is a waveguide for Rossby waves that have an impact on atmospheric rivers and rainfall variability. So when we prescribe high latitude variability, this is the additional skill over AMIP trope, so additional skill. As you can see, of course, a lot more skill in the Arctic, but the skill spreads well beyond the nudging area that stops at 65 north and into the mid-latitudes. So this is the total skill in AMIP-TRHL on the right compared to AMIP. Again, AMIP is when we prescribe observed SST, we nudge the tropics and nudge the high latitude variability to variability in MERA2. And this is the skill for precipitation, where now we correlate precipitation in the experiments to CPC data over the continental US. We see that in AMIP, we have quite low skill over the southwest, and the skill is better in our TRHL simulation. So here's a time series of the so-called skill, which is not prediction, but how well the model in different configurations represents the observed variability in the North Pacific. So this is the region where we're doing spatial correlation over this region that we call North Pacific, North America domain. And in green, we have the time series of the spatial correlation of Z500 in the domain, North Pacific, North America domain in AMIP. So AMIP is able to represent really well the two major El Nino years here, 1983 and 1998, but other years are not so good. And the average skill over the whole period is about 0.4. This shows the average skill. When we prescribe the tropics, that's the orange curve here, we do much better. As you can see, then the correlation goes up to 0.74. And when we in addition nudge the high latitude areas, we get 0.85. So perhaps not completely unexpected, since we're constraining the flow both in the tropics and the high latitudes, but interesting nonetheless. So the bottom line is that we find both tropical and Arctic atmospheric variability influence weather and climate over the North Pacific, North America domain, and they represent additional sources of S2S predictability for seasonal forecasts over only sea surface temperature, or the AMIP conditions. So does this help in tracing precursors of mid-latitude atmospheric patterns that influence Southwest US rainfall? Well, it's interesting to decompose the variability into timescales, so we can look at how the atmospheric circulation is represented at different timescales. We filter the daily data into 4 timescales: the synoptic or weather timescale at 1 to 10 days. Then we have the S2S timescale that represents atmospheric variability between 10 and 90 days. Interannual variability, in this case, is just the seasonal mean, November to March seasonal mean. And for multi-year, we use the low-pass filter to only keep variability above 5 years. We then compute pattern correlations between the observed and simulated Z500 anomaly in the North Pacific, North America domain, now after time filtering the daily data. If the correlation is greater than 0.7, the event is classified as accurately represented in the experiment. In this way, we can count the number of accurately represented events in each experiment to measure the impact of tropical and high latitude nudging. So in addition, we also composite by MJO phase for synoptic and S2S timescales. For the interannual timescale, we composite by ENSO phase, and for the multi-year, we composite by IPO or interdecadal Pacific oscillation phase. So again, we're looking at spatial correlation at 500 hectopascal over the NPNA domain, like shown before, but now counting the number of events for each timescales. Now, for the synoptic timescale, for example, we're looking at daily Z500 anomalies, and we compare to daily Z500 anomalies in MERA2, and counting how many daily anomalies are well represented, where the criterion is 0.7. So the reason the number of events differ on the y-axis is because we're counting, here we're counting daily events, here 10-day events, and here we have 37 years, and we lose some years when we do the time filtering. But what is interesting here is that the weather timescale, the simulations don't capture any variability. So what we have is really not linked to any weather timescale adjustment, but most of the benefit that we get is at the S2S timescale. So focusing on S2S, and here it's color-coded according to MJO phase. So we see that in AMIP, we are not able to represent atmospheric variability at that timescale. But when we nudge the tropics, we have a fair number of events that are well represented in the model. They are so when we decompose into MJO phases, we also see how each phase. And furthermore, when we nudge the high latitudes as well, so this is just a trope, we get an additional benefit. As you can see, more than half the events are well represented in this case. So for the interannual timescale, of course, AMIP does much better because here the influence of sea surface temperature starts to show up. Here's AMIP. AMIP trope, additional benefit from nudging the tropics, and we get definite benefit at this timescale as well, and also from a high latitude nudging. And also for the multi-year timescale, we have benefits from nudging both in tropics and high latitude, especially in the tropics. So we can use these experiments to evaluate the intermittency in the El Nino teleconnections. Here's the year 1983. It was a typical El Nino year in the sense that it brought the precipitation over the southwest US. We have the observed Z500 anomaly here in from MERA2 data. And here is what we get with just AMIP, not too bad. Here's the correlation. And this is when we constrain the tropics and when we constrain the high latitude as well. So we see that all the simulations are able to capture the big trough over the North Pacific. And all the experiments simulate the excess of precipitation. The blue line indicates the observations. This is the precipitation. terms of standard deviations in observations. And we see the distribution among the 10 ensemble members here in each experiment. So AMIP, so even though AMIP already indicates an excess of precipitation, by constraining the tropics and high latitudes, we reduce the spread of between ensemble members here in AMIP-TRHL. So if we look at 2016, it's a different story. Again, Z500 anomaly observed during that year on the left here, upper panel. This is from reanalysis. This is from AMIP. As you can see, the trough is tilted a different way. It doesn't look like the observed trough. And we do get the tilt of the trough here in AMIP-trope and AMIP-TRHL, and correspondingly higher correlation. And as a result, AMIP simulates an excess of precipitation, while the two AMIP-plus experiments are more in line with observations. So we get just normal precipitation or close to zero anomaly in precipitation over California. That means by nudging the tropics, we're able to have a more realistic ENSO teleconnection in the model than when we do not nudge the tropics. So what is going on here? So we do have greater S2S variability in 2016 than in 1983, as I'm going to show now. So the two rows here are for the 2 years. This is 2016. This is 1983. And what is shown here is intensity of subseasonal variability. So we are filtering 10 to 90 days and have depicted stream function at 250 hectopascal, or wave train activity in shading, and velocity potential at 850 hectopascal, or convective activity for November to March 2016 here on top. So this is in the AMIP run, okay? When we nudge the tropics, we increase the subseasonal variability, so convective activity in the tropics. That's indicated by the red contours. So this is increased velocity potential in the tropics here over the maritime continent and Western Pacific, tropical Western Pacific. However, in 1983, we had actually reduced convective activity at the subseasonal timescale in the tropic, all over the Pacific, in fact. Similarly, looking at wave train activity, we had increased wave train activity. This is the stream function, increased stream function standard deviation in the extratropical Pacific here, whereas that's not the case in 83. So subseasonal variability in large-scale circulation patterns in the North Pacific also reduced in 1983. So suggesting relatively weak tropics to extratropics teleconnections at the subseasonal timescale. So therefore, the circulation patterns in these areas were more influenced by subseasonal tropical variability in 2016, which reduced the longer-term seasonal impact of El Niño compared to 1983. So shown here is the correlation between Southwest US rainfall and the Niño 3 index in AMIP. Let's first look at, this is for observation. So this is the correlation between Southwest US precipitation index and Niño 3 index. This is what we get in AMIP, so much higher correlation. When we nudge the tropics, we do get somewhat lower teleconnection, reduced when we nudge the tropics. So the takeaway points from this part of the talk, tropical variability exerts strong influence on the North Pacific, North America atmospheric circulation from subseasonal to the decadal timescales. Imposing high latitude variability further increases the skill of the model. Now, this is experimental work, but it shows that there is potential to improve predictability in Southwest US precipitation at seasonal and S2S timescales if we improve the seasonal or subseasonal prediction, especially in the tropics, but also in high latitudes. And we find that a signal at one timescale may be a source of noise at another, because in our simulations, we find that the ENSO teleconnection is stronger in AMIP mode than in the AMIP-plus simulation. So when we don't have enough subseasonal variability. So when we add the subseasonal variability in the model, we are in fact weakening the El Nino teleconnection. So we weaken the potential for seasonal forecasting. So we tried to pursue this idea of what may benefit subseasonal forecast, may be detrimental to seasonal forecast using the CSM2 large ensemble, but MJO activity and the resulting teleconnections are still not represented sufficiently well. Perhaps more importantly, we found significant model biases in representing the mid-latitude background flow. So this is described in a recent paper by Cameron Dong in Journal of Climate, just out, where he finds that CSM2 large ensemble shows teleconnections associated with southwest rainfall that favor the meridional wave trend, whereas reanalysis shows the circumglobal wave trend as being most important, and links the biases to differences in background flow, where the jet is southward shifted and not extended enough in mid-latitudes. So I am not going to talk about CSM2 large ensemble and its biases. Rather, I'd like to talk about some current work that Cameron is doing, looking at biases in the hindcasts of some of the S2S models. So we're looking at 5 models, which were chosen based on data availability over the period of 2001 to 2015, that they include ocean coupling, and the hindcasts are at least out to 6 weeks, because we're trying to look at the monthly timescale, so averaging 3 to 6 weeks hindcasts. The models are listed here, and they have 7 to 11 ensemble members and are initialized at least once per week. The ECMWF model is initialized twice per week and has 11 ensemble members. To evaluate the subseasonal model performance, we use ERA 5 reanalysis data, where for each model we subsample to the model dates, calculating anomalies in the same way as each model. We composite a monthly wet Southwest US cases, so we're taking the ensemble members with the top 30% rainiest ensemble members, averaging during week 3 and to 6 of the hindcast, and taking initializations from November through February, so November, December, January, February. The figure shows composites for the 200 hectopascal field of meridional wind in shading and stream function in contours. Precipitation anomalies south of 20 north are also shown. So we see that for ENSO, for the ERA 5 reanalysis, the meridional zonal wind anomalies over the East Asian jet are indicative of the circumglobal wave train, whereas the models mostly show this meridional signature, all of them, except maybe the CNRM model that shows ridging over Alaska. In order to more clearly decompose the various patterns associated with Southwest US precipitation, we use a Gaussian mixture model to cluster circulation patterns in the North Pacific. And we find the best results with these 3 clusters shown here. the meridional pattern with strong tropical precipitation, El Nino-like, if you will, and the zonal pattern, and the arching pattern. The zonal pattern is reminiscent of the circumglobal wave train of Brandstatter, and the arching pattern is somewhat similar to PNA. Looking at the cluster frequencies, so that's in here, meridional, zonal, arching. The models are shown here in the colored dots. Era 5 reanalysis is shown in stars. Okay, stars. So, and the ensemble mean is shown by the black diamond. You can see that the models are under predicting the zonal pattern shown here, and over predicting the arching pattern. Looking at the model background flow biases and contours and the Rossby waveguide computed as in Hoskins and Ambrissi, it's the linear sense. This has been used a lot. It gives an indication of how strong the wave or how extended the waveguide is. We see that the models have less zonally and northward extended waveguides than the reanalysis. You can see this goes. This is for wave 5 here, whereas the models is more truncated over the Pacific, further west. This means fewer Rossby wave trains, so wave number 5 or so, make it to the west coast. The representation of subseasonal tropical variability, especially the MJO propagation, remains unsatisfactory beyond week 2, as can be seen here. The propagation is too weak compared to what's seen in era 5 reanalysis for all the models, really. And finally, to examine how MJO representation affects Southwest US prediction of rainfall, we plot Southwest US precipitation as a function of forecast lead time here, and initial MJO phase for active MJO events. So in reanalysis, there's a clear propagation signal. So here's phase 5 with the lead time of about 10 days. There is, so starting from 10 days after phase 5, there is a positive precipitation anomaly. And as we move backwards in initial MJO phase, the positive precipitation anomaly moves out to longer lead times. So this indicates its association with the MJO as far as 35 days after phase 1. So when we compare to the models, we find that none of the models display a clear propagating Southwest US precipitation response. So if models could replicate the coherent propagation and strength of the MJO convection patterns, then we might be able to increase skill. These are the main Pacific teleconnections associated with Southwest US rainfall. The circumglobal pattern is underrepresented in the models, and the arching wave train is overrepresented. The discrepancies may be due to jet biases and due to remaining problems in representing the MJO. So I want to move on to the last part of my talk. Case study of the puzzling water year 2017. This was a pretty amazing year here in California. It was very wet and absent any obvious climate forcing such as El Nino. Just for comparison, on the right is the accumulated rainfall in water year 1983, which was the record El Nino year. So this shows observations. On the left, we have the precipitation anomalies and shading, surface pressure and contours. And the arrows show 700 hectopascal wind anomalies from October through March now, 2017. There is a well-placed trough here just off the west coast with onshore flow and plenty of precipitation. On the right, we see anomalies in 250 hectopascal zonal wind in shading, and Z500, Z250, excuse me. They're both at 250 hectopascal this time. So shading is this extended jet here, and the this circumpolar wave train. So this year was marked by a strong zonally extended jet and a wave 5 zonal wave train. Now we ran this case with our AMIP and AMIP-plus model configurations, and here are some results. So this is only AMIP, and as you can see, this is observations on the left and outcome from the model on the right. As you can see, a ridge of the west coast and dry conditions. So SST has minimal influence in this case. What about nudging the tropics? So this is AMIP trope, when we nudge the tropics to observe variability. Makes things worse, even a stronger ridge here and drier. So what's going on? What about high latitudes and influence from the high latitudes? Well, we do get the trough here, even though it's displaced to the north, and precipitation anomalies, and we get a zonally extended jet. So does that mean that there is influence from high latitudes? This is when we nudge both the tropics and high latitudes, and yes, the anomalies are stronger in this case. Both the trough and precipitation anomalies, and this jet is stronger. These anomalies get closer to observations as we nudge both tropics and the Arctic. Is it possible that there is some influence primarily from high latitudes? We actually just ran this case. We only had MERA-2 and reanalysis through 2016 when we ran the original experiment. We just got this, and we have by no means done a thorough analysis, but there was no stratospheric sudden warming that winter, 2017, and only weak strat-trope coupling in the Arctic. However, Siberian snow cover was anomalously high that fall, possibly promoting a stronger jet. But as I said, we're still looking at this, and yes, definitely the possibility of influence from high latitudes. I'm actually going to do some advertising here. So I thought this might be a good opportunity to advertise a program that will take place at the Kavli Institute for Theoretical Physics at UC Santa Barbara for 10 weeks, actually from a year and a half from now, from spring to summer 2025, so next year. This is a program on the physics of changing polar climate. And I'm one of the coordinators, along with excellent people, Patrick Hambach, Paul Kushner, Mathieu Morlingham, and Hélène Saroussi. And we have great scientific advisors. And I'm hoping to get interest from different members of our community interested in this program. Motivating questions: what are the causes and consequences of polar amplification? What is the role of polar feedbacks in this amplification, and global implications? We also looking at transport of energy, moisture, and constituents to and from high latitudes. There is an urgent needed improvement in representation of polar processes in modern Earth system models, and the need to carefully design and coordinate polar observing systems, unify many of the activities taking place in in different groups in our community. So, and we want to capitalize on emerging data science and machine learning, artificial intelligence approaches to exploit data. And this is a tentative, it's a 10-week program. So this is a tentative structure of the program. Foundational material will be presented in weeks 1 to 3. Review a more technical state of the art in polar science will take place in weeks 4 to 6. We haven't really refined details beyond this. This is not usually how planning is carried out in KITP programs. However, we're really hoping to see a good mix of observational modeling and theoretical researchers present throughout the program and not have any particular weeks focused on, say, observations or models or theoretical work. So this is the website for applications, and actually they want applications in over a year before the program starts. So I'll stop here and take your questions.
Thank you. So now everyone is able to unmute themselves, or you can raise your hand and ask a question. Or if you don't have a microphone, you can type it in the chat and I'll read it out loud. Any questions? Well, if there's no questions, we can end early, but
actually, I've been trying to expand the screen and I haven't been able to. This is Louis Uccellini. I have a couple of questions, if I may.
go ahead.
Hi. So first, it was a great presentation. I was intrigued by your application to 2017 and was wondering if you have taken a look at 2019, which also was a very anomalous year with a very heavy precip, and it appears that the cross-polar flow, those Arctic troughs that were amplifying that year, and then some, especially towards the end of winter, were retrograding, providing the westerly flow for California with their Northern California, especially with their massive precipitation later in the winter. So I was just curious if you've taken a look at that, because it appears that the Arctic flow regime was a very dominant factor in that year.
Yeah, no, thanks for that. Thanks for that suggestion. We haven't taken a look. We're just working our way back. So we need the MERA reanalysis data is nice because it's 3 hourly, so it's really convenient for nudging the model because it's available more frequently, and we just recently got access to the later years, so we will be looking at more cases. It's really interesting because you can eliminate certain things, and yeah, we're planning to do that, in fact.
Yeah. So when I was still in NOAA at the time, and I was the chair of the Weather, Water, Climate Board that they got all the line officers working together. We were able to put together a grand challenge hypothesis to try to move forward as precipitation prediction. And there was a focus on 2019 looking at that perhaps the cross-polar flow is a greater source of predictability issues than the west to east flow across the Pacific. You know, put a hypothesis out there that would get people's attention and then
So what do you mean by cross-polar?
Well, that you get the amplifying ridge up over Alaska, and you get a very strong flow over the top of that ridge, and you can get these critical radius of curvature, which the downstream flow with the trough downstream of that ridge axis actually can cut off and retrograde, and which is what was happening several times, but definitely during those periods of very heavy precipitation in the March, April timeframe. It was a curious thing. I made a presentation to the U.S. Global Change Research Program in October 2020, and I think they've got that on file. You might want to take a look at that.
Okay.
I'm not sure many people have done anything with it, but it was clearly one of those anomalous years in 2019 with very, very heavy precipitation coming out of this interaction between the polar flow and, cross-polar flow, getting down into the mid-latitudes and tapping into the moisture out of the Pacific. So that might be an interesting thing to look at since you're actually, separating the tropical and the mid-latitude or polar regions. Be interesting to see what kind of signal you get for that year.
That's a great suggestion. And I would love to be in contact with you. Are you still, do I have your email address? No, I don't think so.
No, I'm okay. I got a Maryland address, and
I'm typing in my email. If you could send me a message, then we would be in contact. It would be great.
Okay.
I would love to, I would love to hear.
Yeah, I remember we talked when I visited Irvine a couple of years ago, many years ago, actually.
And you didn't think much of atmospheric rivers, if I remember correctly.
Yeah. Okay. Yeah, I'll get a hold of your email address from Cassie, and then I'll write to you.
Please do, because I'm very interested in getting your opinion and getting suggestions from you. I would love to hear from you.
Okay.
And you might want to join us for the program. Now you have time, right?
Yeah. Okay, we'll talk about that.
Okay.
I'll connect you to once the seminar is over. I have both your emails, or at least I have Louis, and I can get your email right when we're done. So there were two questions in the chat that I just want to put your attention to before we wrap up. So Christine asks, can you post the polar workshop information here in the chat?
Oh yeah. Is it Christine Shields?
Yeah.
Yes, I can just let me type it in here.
Great. I definitely have some folks that I collaborate with that would probably love to participate in that.
Yeah, of course. Where is it here? So it's KITP.
Here. I'll do it. Go ahead.
Oh, okay, great.
Yeah. Stay on this slide. I'll type it out.
25. It would be great to have people who are looking at different processes because dynamics are really different at high latitudes. There's this shrinkage of scale. Rossby waves behave differently with Rossby wave packet. It's very different. So I'm really looking forward to it. Being able to work with different people and having input from different communities. So it will be really interesting. And we have plenty of time. We have 10 weeks. And I'm planning to be there the whole 10 weeks. I'll be on sabbatical.
There's another question. Are you planning to further split AMIP trop to replay different tropical regions? For example, Indian Ocean and Pacific.
That's a good question. We actually did that for one of our studies. So we were interested in MJO interaction with QPO for 1 year. There was this really intense MJO year, 2012, 2013. We nudged the tropics going from, I think it was from the Atlantic over Africa over to the maritime continent where we set the atmosphere free. So we basically, we charged the MJO and then let it go because we were looking at how it influences, how the combination of MJO and QPO affects precipitation. And we were actually looking at South America in that case. There was another graduate student who was working on the South American monsoon and wanted to see that effect. And she wrote a paper in GRL. And actually, I listed that paper, even though it's not related to California precipitation. We're a small group. We can't do everything. And so she ended up doing this study, effect of the quasi-biennial oscillation on the Madden-Julian oscillation teleconnections in the Southern Hemisphere. So we did do it, but it's, so what we did was we did it for the year 2012, 2013. That was a Eastern QBO East year. And then we used the previous year, that was a West QBO year, and assigned that QBO and looked at the difference. And it was interesting, but it's difficult to, I mean, the MJO kind of withers out pretty quickly, but we did get that effect for that case. Yeah, you could do that. And especially, this is an old model. It's pretty coarse. It's only 2 degree. We want to do this in at least a 1 degree model. Yeah, we would like to do that. Yes, sure. We have all the tools. We just need some funding and manpower, woman power.
Michael asks, was that experiment also run for DJF or NDGFM?
It was run for the winter, yes, for the Northern Hemispheric winter. So she was looking at the effects on precipitation in the South American monsoon system, which is the southern winter. So it was for the winter time.
Thank you. Do we have any other questions before I wrap up? Okay, well, unless I am interrupted, thank you so much to Professor Magnusdottir for coming to speak to us today. This was great, and thank you to everyone for showing up. The video will be on our YouTube channel in just a couple of days. Dr. Magnusdottir, could you send me your email really quick just so I can connect you? Here, I'll send you a chat.
Okay, yes.
Here, so then you can click my name and just send it directly towards me or to me.
Okay.
But anyway, thank you, everybody. Have a good afternoon.
Okay, thank you. Thank you
got
so
it.
much. I enjoyed it.
Okay, great. Well, have a good day, everybody. Bye-bye.
Thank you. Bye-bye.
Okay, Cassie,
yeah?
You'll send that to me, right?
Yeah, I'm doing that right now. That's why I got the
great.
email.
Thank you. You guys, good seeing you again.
Yeah.
See you, Louis.
Right.
Take care. Bye-bye.